Okay, let's start our webinar. I hope you can hear me really well. So today's webinar is about week 2, and we are going to talk about some advanced things that are connected to regression models. So in week 2, you could see different models that are somehow linear. It can be, as we have linear regression, which tries to linearly explain the target variable. And we have also linear models for classification. But the goal for today's webinar is only about regression models. And the main part is some maybe advanced methods or advanced knowledge. There will be 2 parts about today's talk. The first part is some interesting explanation for regularization. And second part is how we can use other algorithms for regression. So for other algorithms, you may have already seen like different algorithms besides linear models, such as decision trees or ensembles, etc. And you may well know how to apply them, how to you understand what are these models. But it's interesting also to see that almost all classification models can be used for regression problems. Okay, let's move on with that. So first, just to remind you what mathematical model we have as regression model. Basically, the problem is that we're trying to predict continuous variable, so some kind of number. It can be price of the house, it can be price of the car, it can be some other value like profits or anything basically. And we have an approach that is called ordinary least squares, which tries to minimize the square of error, or to be more precise, the sum of squares of errors for each object in our dataset, in our training dataset. And we have 2 models that are called regularized models. It's rich regression and lasso regression. These models use regularization coefficients, lambda, as it is put on the slide, which somehow control the behavior of the model. And if we increase the parameter lambda, we make the model more strict. In a sense, we try to decrease the complexity of the model and try to make it more sensible in a way. We may understand in a way that how we can control. So it's reasonable if we want to minimize given expressions, we have to minimize the squares. And if first part of the expression is constant, the second part we can change by changing lambda. And of course, if we want to minimize the overall value, we want to minimize the value of coefficients beta. If you have like high value of lambda. In this way, we can understand that increasing the lambda value, we decrease the value of coefficients, and this somehow controls the complexity of our model, makes coefficients more maybe not like good term, but the coefficients are more shy. They don't try to be too fit for training samples. Yeah, there are also like 2 two properties, one for each regression, one for lasso regression, that we understand and that we can use. That with reach we have exact solution, we can always get it, and with lasso we can use this regularization for future selection. However, the interesting thing here is that we do not have a straight explanation for lambda coefficient. So for the value of lambda, we just think about it as a coefficient. Like we increase it, we make regularization strict. We decrease it, we make regularization less strict. So how can we make a good interpretation of this hyperparameter, and does it make some sense? And actually, there is one approach which, not in a direct way, but it shows the meaning of this regularization hyperparameter. So how does this happen? There are different approaches to regression problem, actually. But besides the approach that we described, ordinary squares or OLS, we also have a probabilistic version of this regression and of regression model. And this probabilistic version actually gives us the same result as linear regression. So just going back to the previous slide, this ordinary least squares approach is actually the same as probabilistic approach. So it gives the same result by slightly different assumptions. And in the probabilistic approach, we are trying to maximize so-called likelihood of the parameters. So you can see here is a formula, which we also will describe a little bit later, which is called Bayes' theorem. Some of you may know it, but I will try to also explain it so it will be clear for everyone. And in this formula, we have several parts, and one of the parts is called likelihood. Basically, it means that we are trying to find parameters theta, such as our data y would be the most appropriate. So basically, we're trying to fit parameters theta, which would be the most appropriate for current data that we observe. And in this probabilistic approach, we actually get the same answer that we get in ordinary least squares approach. So if you remember it, it's just multiplication of some matrices X and Y. So in sense, it is the same. However, besides direct estimation of likelihood, there is another approach that's called Bayesian approach, which uses Bayes' theorem instead of likelihood. So Bayes' theorem is, you can see it on the slide. It contains several parts: posterior, likelihood, prior, and evidence. For now, we only need to, we don't need to understand evidence, which is just like overall probability of getting the data, but because it's always constant, it doesn't depend on theta, as you can see from the equation. We just do not need to understand what is it and how does it work. So the important parts here are likelihood and prior. Likelihood we already know. This is something that we try to maximize, or this is something that we estimate through the parameters theta. So basically, this is the probability of getting the data y when parameters theta is true. But actually, another thing that is prior is important part here, because prior describes the distribution of parameters itself. So this equation, it tries to estimate not only how likely is to have our data given the parameters, but also the probability to obtain such parameters. So basically, maybe our data is good for chosen parameters, but actually chosen parameters are really unbelievable. Like their value is too big, or they have big differences, or they are too similar to each other. So there are a lot of possibilities where we can say that parameters that we get are actually not believable or just wrong. So by multiplying likelihood and prior and dividing by evidence, we get so-called posterior distribution. So this is distribution after, or like the probability distribution in the case when we already know the data and know the parameters. This posterior distribution, it depends only on the parameters. So because the data we already know, the data y is always constant. And what if we try to maximize the posterior distribution instead of likelihood distribution? So basically, instead of trying to maximize the probability of our data, so instead of trying to feed the data as much as we can, we trying to estimate the parameters in such a way that not only the data has high probability, but the parameters that we want to get also have high probability. So in this approach, when using such theorem, such formulation, we need some assumptions. So we still need the probability of so-called noise. So we already know that noise is distributed normally. It is known even before we use Bayesian approach. Also, there is assumptions about the data. Assumption is as follows: that it is normally distributed with average given by data x multiplied by coefficients beta. So this can be explained as follows. If we have the noise epsilon, then our data is distributed as basically linear regression formula, x multiplied by beta, plus this noise. So actually, those formulations, when we have epsilon distributed normally with mean 0 and y distributed normally with average x multiplied by beta, this is the same formulation. And the second assumption we need to have to understand the distribution of prior. So this is a distribution of coefficients theta. After that, there are some calculations. They are actually really simple. If we want to maximize the posterior distribution, as it is written here, theta MAP, maximum a posteriori distribution, and all a posteriori parameters. And we need to maximize it by using parameters theta. Then you can see that we do not need the evidence, so-called. And also, if we take logarithm out of this expression, which we can always do in such cases, we can split this expression in two parts. Basically, it will be sum instead of multiplication. So now the only thing we need to do is to, instead of abstract distributions that we have in this expression, we need to put some like real data or real distributions. we already assumed that distribution of data is normal. So instead of logarithm of p of y on parameters theta, we can put normal distribution formula or density formula. And we also need to choose a prior distribution for the seconds part of this expression. So let's assume again that the second part of the expression is also normally distributed. So the prior also normally distributed, and the distribution of coefficient is Gaussian. In a sense, it means that we want the coefficients to be close to 0, and the probability of coefficients or parameters of our model being far from 0 is low. And we can also say that we can also set the parameter, like the variance parameter for the distribution, which would control how far the coefficients can actually go. So we can make this limitation. After that, now we can just put in the formulas in this expression, and we get also some kind of calculations. Formulas may look, again, a little bit scary, but at the end, it all goes down really well because we maximize this expression over beta coefficients. And it means we also use logarithm of the function, which actually makes less problems for us. And as a result, we get the following expressions that you can see in the fourth row. First is the sum of all objects, and we have a square of difference between target variable and linear regression, which you can see beta multiplied by x. And plus also some coefficient multiplied by the sum of beta coefficients. As you may notice, this formula is exactly what we have for rich regularization. So to summarize, by using Bayesian approach and by applying some assumptions to the data and to the prior distribution of coefficients or parameters of the model, to be exact, normal distributions for both, we actually obtain exactly rich regression. And what is good from this result is we can now interpret the coefficient lambda, because the coefficient lambda is actually a fraction of two variances. The sigma squared is variance of the data, and theta squared, tau squared is the variance of coefficients. So how do we interpret it? We assume again that data is constant, so we know that sigma squared is always constant. Then we can change tau, and if we increase tau squared, it means that coefficient lambda decreases, and by increasing tau squared, we actually increase the range of possible coefficients that are allowed by normal distributions. So we make a connection between decreasing lambda coefficient and increasing the range of values for coefficients beta. As you can see, this is exactly the goal of our regularization, exactly what we already described, but never never gave it a sensible explanation. If we again reverse the situation and we start to decrease the coefficient, decrease the variance tau squared, it would mean that we limit our coefficients beta stronger and stronger, and they have less variance, they have less range, and the regularization in this case is more strict. This result we get for rich regression, but also we can get lasso regression if we use another prior. So instead of normal distribution, we use Laplace distribution. And by putting it in the same expression, in the same way, we, in the end, obtain not beta squared, but absolute values of beta. And this would be lasso regression, and we can also have a similar explanation to it. So just to, again, summarize, we have this all explanations on one slide. Good practical application of this knowledge is also that because we know the data, we can estimate its distribution, we can estimate its variance. And because we also set each parameter as we want, basically we have 3 variables in an equation, and we know 2 of them. So we can calculate the third parameter, which would be the variance of coefficients. And as a result, we know the distribution of coefficients. So it would be normal distribution with average 0 and variance, some calculated variance, tau squared. And using this information, we can calculate a so-called significance or p-value for each of coefficients and understand the importance of each of them. So it would give us information about how rare is the case that we get such high coefficient, for example, or like such high in the means different from 0. And also what we need here to remember that all this work, all this result, we only get because we decided on some assumptions on the distribution of data, on the distribution of coefficients, and another demands for linear regression, such as linearity, homoscedasticity, etc., they all still here, and we need to follow them strictly. Otherwise, all our results can be invalidated. So if you have now any questions about this part, please ask me about it, because then if there are no questions, we just go to the next part of our webinar.
Why does it say that only in theory we can estimate parameters of coefficient distributions?
Sorry, where does it say?
Well, the second point on this slide.
Okay.
It says in theory. Why in theory?
Because
does it mean that we can't do it in practice?
Yeah, no. We can do it in practice. Yeah, it's all right. It's just, again, the result is so as I described, it is clearly possible and it works. But in theory, we also need to remember that if our data is not actually normally distributed, it would mean that our result is just, invalidated.
Oh, okay.
So in theory, we know the data and we can assume that this is from normal distribution. But if you check the data like against some test for normality, and you see that the data actually not normally distributed, then you cannot use this like in this sense. I mean, you can use it, just put the data into the formula, but the result you get, you understand that it doesn't work.
Yeah. Thanks.
Okay, any other questions? Let me quickly check if there are some questions in the chat. Okay, I don't see any. All right. Now let's continue with it. So this was a description of like another approach to regularization, which gives us the same answer almost, which may be more useful as explanation for regularization. Now we go to some algorithms that you learn through this course actually, and it's actually possible to use these algorithms not only for classification problems, but also for regression problems. This is important because when we use linear regression, the main struggle with it is almost like not almost, but 80% of struggle with it is only linear. So to understand some nonlinear dependency using linear regression, you need either feature engineering to create new features to make, for example, polynomial regression, as it was shown also in the lecture, or maybe some other kind of features. And even this is not always giving you the same result. But using some classification algorithms for regression can give you the needed nonlinearity, because many of the algorithms are more flexible than, you know, linear equation. Actually, all the problems that I described about nonlinearity, about heteroscedasticity, it's all like problems of linear regression, but some classification algorithms are immune to that, and we can use them to mitigate this problem. So basically, if you check the data, for example, and you see that the data is not normally distributed, maybe you should use algorithms that are not linear and not linear regression, because we use linear regression only with assumption. Maria, yes, please go with the question.
Yeah, hello. So just forgot about my question. On the first slides, you had information about polynomial regression. And there was an example with feature engineering. So for example, we have two features, x1 and x2, and then we like to come up with some new features like x1 squared, x2 squared, and their multiplication. And do we get rid of original features x1 and x2 in this case?
Good question. Actually, in most cases, no. The reason is because when we create complex variables, as you described, like x1 squared, x2 squared, or multiplication x1, x2, despite the fact that they can bring new value to the data, new specific, new patterns, at the same time, if we don't use the usual x1 and x2, we lose them as information, because by multiplying them together, they may become more like dependent on each other mostly. Like just an example, if you have x1 and you make x1 squared, you understand that you lose all negative values.
Yeah.
So basically, if you have values, for example, -5 and 5, for x1, they will be completely opposite, but for x1 squared, they are the same. So as a result, we lose this, interaction between them.
So in this case, we lose just some significant information for our prediction.
Yeah, so usually it doesn't happen. We do not get rid of variables of low cardinality, or not cardinality, but low degree. Yeah.
Okay, thank you very much.
Yeah, no problem. So let's get back to the current theme, current topic. So as we said, we can use classification algorithms when we have data that is not appropriate for non-linear, for linear models, for linear regression mostly. And like classification algorithms that we know, classic classification algorithms, can be transformed to solve regression tasks. Some of them can be done really like in an intuitive way. Some of them are much more like for some algorithms it's harder, but it's still possible. So let's just go one by one and see. So let's maybe get a bit interactive here. So if you have the k nearest neighbors, so just a question. So do you already know this algorithm? Like, have you like get introduced with it? I mean, k nearest neighbors. Do you know what is this algorithm? I see plus in the chat. Okay. Okay, so if some of you already know what is this algorithm, we know for classification, what we do. We have a number of points, and we make a prediction based on the neighbors. And if nearest neighbors belong to the same class, this class would be prediction. How would we change this algorithm so it would predict continuous variable? Any thoughts, ideas?
Sarah, I have an idea. Maybe we need to order our observations somehow. And so then we need to choose the closest according to the value.
Okay, but what do you mean by order? Because if we have not one-dimensional data, but we have 2 attributes, 3 attributes, how do we order them?
I don't know, maybe to, if we have numeric features, just to combine them somehow to have this standardization procedure, and well, have the regression task, so we have some values, we can compare them. But yeah, I have some mistake of the.
Okay, so let me just give you a hint. So we do not need to change actually the definition of neighbors. So the algorithm stays the same in that part. So basically we find, for example, 5 nearest neighbors. But the only thing we change is that we do not calculate the majority of some class, but we do something else. So imagine that instead of class given to each point, we have some continuous value given to each point. So how do we make prediction based on that?
Maybe we calculate the average of k nearest neighbors.
Yeah, I see exactly the same answer also in the chat. I don't know if it's you or maybe like
oh, no, it's not me.
2 ideas come together. So yeah, exactly. This is really simple and intuitive. We just take the same approach as k nearest neighbors classifier, but instead of finding the majority for some class in the neighborhood, we just find like average of these continuous values in the neighborhood. So if you have 5 neighbors, we have 5 values, and we just average them and get the prediction. It's really intuitive because imagine that we have a task of predicting the price of a house. For just like for any person, how would we go about it? So imagine you have to sell your house, or yeah, just sell your house, but you don't know how to estimate for how much you have to sell it. So how much money you can make by selling your house. So you go to some kind of site and you check the prices of similar houses. Yeah. So you find houses with the same number of rooms, with the same number of, I don't know, bathrooms, with the same area and situated like near you or in the same district, etc., etc. So basically you find neighbors. It like maybe figuratively, but maybe directly neighbors. And you see that these neighboring objects, they have these prices. They vary slightly, but you just average them because you want to get some kind of, you know, not you don't want the value to be too big, or you don't want the value to be too small. So this is completely perfectly intuitive for such situations. Can you introduce regularization for non-parametric model like KNN? It's actually a good question, but unfortunately, yeah, because it's non-parametric, it is hard to say how we can regularize. We can change some hyperparameters, but it's not regularization. So instead of treating each object as the same, we could say that if the distance between objects is high, the influence of this neighbor is low. But it's not exactly regularization, it's just the way we calculate the influence of each neighbor. And doing such regularization is hard. However, there is one way which actually crosses with SVM or support vector machine. There we can use kernels, and kernels actually play a role of regularization somehow. And in KNN, because we calculate distances between couples of objects, we can actually introduce kernel functions to calculate distances instead of direct, you know, calculation of distance. So it would be like similar to SVM. However, the effect of this, I wouldn't say it can be good or bad, because embedding embedding objects in a higher space makes them equidistant from each other. Usually, it's like what usually happens. And if you make it equidistant, it means that any point can be neighbor of any point, which breaks the KNN algorithm basically. So SVM in its works uses kernels, and kernels actually play sometimes regularization role. But for KNN, I don't see that it can play regularization role. So to summarize, to answer your question, I don't think we can regularize KNN without introducing some kind of parameters and then regularize them. I think there are maybe articles about it who like scientifically try to improve KNN algorithms or make them better. But unfortunately, I'm not familiar with such articles, so maybe you can find them somewhere and there will be some interesting approaches. Unfortunately, I don't know about them. All right, yeah. So now to summarize KNN regressor here. It's quite simple to use because it's almost the same as KNN classifier. It's evident, it's obvious, it's intuitive. However, it has all the problems of usual algorithm KNN classifier. So again, it's not used usually because it does not have a good quality when we talk about metrics of classification. Okay. Next on our list is decision trees. Again, so I hope some of you already know this algorithm and it's in your works. So the question here is, how can we change this algorithm to solve regression task? Don't worry if you don't know this information yet, because in in this case, you can always look at the lecture that describes this algorithm, and after that you can get back to the recording of this session and like to understand how the regression works. But for now, anyone who knows how decision trees classifier works, how can we change it to solve regression tasks? What changes do we need to introduce? It's also intuitive, but a little bit harder than KNN. Any ideas? Or maybe
we should introduce classes like classes that are ranges of some continuous variable. So if so when we have a decision tree, it chooses where to go. We arrive at a certain range.
Okay. Okay, I see. Actually, you are close to the answer. It's a bit different, I would say, but in a sense, you could see the similarity to what you are describing. So yeah, please.
So as far as I understand, in decision trees, we have nodes, and every node would take a decision where to go. So not exactly ranges, but so we compare values, and also at the ends we have some final values.
Yes.
And there somehow we decide what value can be our prediction.
Yeah, so you see, this is actually similar to KNN a little bit, because you're right, we need to change how we calculate predictions. So instead of calculating the majority in some final node, we actually calculate again average of values in this final node. So this is one actual change that we need to make. So every leaf contains again the set of objects as usual, but this set of objects has continuous values of targets. So their average would be the prediction that is used when like some new object get to this leaf. The second change we need to introduce here is actually to change the measures of information gain. So each split of tree is done by calculating entropy or Gini coefficient when we talk about classification. And this is done for, for classification, for classes, for probabilities. In regression task, we do not have classes in their probabilities, we just have values. So we need to calculate information gain of splitting these values apart. And the role of information gain here can play simple variance of the data. So just imagine that before the split, the variance of data was huge. And after the split, the variance of data in those two sub nodes became small. Basically, it means a good split. So we divided two groups that were far from each other into two separate nodes, which is good. So those two changes we need to do to make decision trees work for regression. Here, what is good in this algorithm? When we use decision trees, we can interpret these trees to get the result. So, all this tree structure is similar to human-like decision structure. And it's simple, we can interpret. The problem, however, here is that in a tree, we have limited number of leaves of final nodes. And as a result, it means that we have limited set of predictions. So either way, when we make prediction, we get into one of the several leaves, and they only have limited sets of values. Like, for example, we have 7 leaves, so 7 values. And as you understand, it's not a very good algorithm when we need to predict some continuous variables that can be between, for example, 0 and 100. And we predict only values 30, 60, and 85, for example. This is not a really good algorithm. It's really strange. And that's why decision trees by itself usually are not used for regression. However, if we talk about random forest and extra trees algorithms, they are more popular in this case. And can somebody say to me, like, how do we change algorithms for regression? How do we change these algorithms for regression? And why it would work much better than just one decision tree?
So again, it's almost the same, but we have just many trees, for example, and we get our predictions at the end, and then we just average the result.
Yeah, exactly. So it's, again, really simple. If we know how to transform one tree to make continuous predictions, we can transform them all. Each tree by themselves is limited in their predictions. But if we just imagine the situations that we have 100 trees in a forest, and each tree has, for example, 4 leaves, just 4, then we can understand that the number of different predictions of the whole forest, which we get by averaging the results of each, like, of these 100 trees, it's actually the number of different predictions is actually 4 to the 100th degrees. So you can calculate by yourself how many zeros this number has, or how many digits this number has. As a result, it's almost not how to say in these cases, we cannot distinguish the result of these algorithms from continuous predictions, basically. So this works all right, and I just can't say anything else except that this algorithm works good. It can be used for regression. It has the same problems as random forest extra trees have by themselves. So, like, bad interpretability as an ensemble. I don't remember exactly what are the disadvantages there. Maybe correlation, but yeah. So I guess it's not a lot to talk here. Okay, let's go further. Boosting algorithms. We know that boosting is powerful tool for classification, and the question is, could we change the boosting for regression task, and how could we do it? I don't want to torture you too much here, because it's actually here is when change to regression becomes a little bit harder. So what actually should we change? The main problem here is loss function. Loss function in boosting algorithms sometimes is, if we take, for example, other boost algorithm, usually it takes into account classes, like for example, -1 and 1. And as a result, we need to somehow change loss, so it would take any value between, well, from So it will take any value for prediction, and we can calculate loss from this. Because of some inner works of boosting, loss should be actually limited between 0 and 1. And 0 here is the best option because the loss is minimal in this case. And usually it means that we should use somehow some kind of exponential loss or softmax loss. Such advances are made. So regression versions of boosting algorithms exist. There is other boost regressor. As I remember, there are gradient boost regressors, XG boost regressor, cut boost regressor. So all these, external libraries also have regressor version. And the process of how the algorithm is transformed, there is not much change, but you need to understand the change in the loss function. This process can be described. Well, I have a link in the presentation. I can give you this link in the chat. Just give me a second. So this link about for the article that provides insights about how we change boosting here. Again, it's a bit harder than I guess decision trees and harder than KNN algorithm, but it's still quite understandable, I think. And of course, it's also used a lot. Okay, and finally, is it finally? Let me check. Yeah, I think it's mostly finally. So final algorithm is SVR, support vector machine, which is called support vector regression, actually, SVR. And here we have a really hard one because change is actually interesting, but tricky. So it's really clever in its idea because it reverses the problem of SVM, but it makes it harder. So if you remember the SVM problem, we need to find the decision hyperplane in such a way that the decision stripe or the space between two classes according to this decision hyperplane would be the largest. So here the situation is vice versa. We create stripe or lane as narrow as possible, which includes as many points as it can inside itself. So instead of separating points by huge empty space, we are doing the reverse. We're trying to collect points in as narrow space as possible. This leads to reverse model formulation. And actually, as it happens, we do not have one decision hyperplane, but two decision hyperplanes. Here they are chosen on the picture as a dashed line, two dashed lines. So basically, any point that lies behind those lines is penalized. So this is a bad point. And any point inside is good. And the closer point is to the estimated model as it line as it is shown on the picture, the less penalties you have. So, oh, actually, non-penalty we have. So the problematic here becomes stronger, and it is solved actually similarly to the usual SVM by solving dual problem, by using optimization theory and all the consequential things with that. So there are some such things as Lagrange multipliers, different techniques are used to find the solution for this problem. Yeah, so that's it. I just have here a slide about summarizing all those ideas here. Yeah, and again, pros and cons here. So pluses and minuses are similar to the support vector machine for classification. Like if you remember, there are problems with efficiency with large data sets. It's actually solved through heuristic and not exactly, which makes it usually perform worse than expected. It is long, like in calculation time. Yeah, and yeah, that's mostly that's the important negative sides of using this algorithm. To finalize, just a little also insight about another regression types. Some of them are again in its base are linear, such as elastic net, for example. This is a fancy name for the simple idea. What if we use not one regularization but two, like lasso and reach together? In some ways, it can be a good idea because lasso part of regularization can select features, and reach part of regularization can smooth the coefficients better. But usually, like when you use it, it's not much different from results of just reach regression or just lasso regression. And of course, it's linear again, so we still have this problem of linearity. Another type of regression is regression that follows the outliers. So there are some types of regression that try to avoid the influence of outlier points. One of these examples is Huber regressor, which uses so-called Huber laws to determine outliers, and their influence on loss function for regression would be different. And their influence as a result would also be different or almost alleviated. As a result, we get basically regression only for important points, not like some kind of mistakes, outliers, etc. Such types of linear regressions called robust linear regressions. So because they are robust to outliers. So this is a simple explanation, simple definition. Some models use another residual distribution. So as I said, if your data is not normal, maybe they have some other distribution such as gamma distribution or +1 distribution. For these cases, there are actually models of regressions, but they are not so known, and well, you can check it for yourself. There are also some kind of specific regression types, LARS, ADR, Bayesian that we actually have, but Bayesian with different distributions is also important. There are some regression types which use splines. We could describe it as linear regression, but divided in several parts. So imagine, let me just actually show you this picture. So this picture describes the data that has several domains. Like one has wide wave pattern, another is constant, and another is narrow wave pattern. So there are 3 domains. And for each domain, we would need like either specific parts of a model to be responsible for the result, such as, for example, random forest does. Or maybe we need to split regression into several parts. Each of the parts is linear, but together they combine into some kind of line that is not strictly linear. So this is the idea behind some spline algorithms. I think the most known here is algorithm that is called MARS, M-A-R-S. So you can also check it for yourself, find the description of the algorithm just to see what are the options for different regression problems. And for now, I think that's all for our webinar. I thank you for your attention. And if you have any questions now, question about this webinar, this information, or maybe something that is connected to lectures about my weeks. My weeks are 2, 5, and 6. Please, you are welcome to ask these questions. I have a question actually in chat. Sorry if I stopped someone. Out of scope question, may we discuss XGBoost in next webinar, at least an intuitive high-level explanation? I think we can do that, but like I have one webinar left in me, and I believe I don't know what is the topic for Maxim's webinar. Maybe actually he wants to cover it, so I'll ask him. But if you want, I can give you a lecture about it. Maybe not exactly XGBoost, but maybe I can try to talk about like known external boosting libraries such as XGBoost, CutBoost, and LightGBM. So let's see about that. Okay, any other questions?
Could you please go again to the Bayesian part of this
yeah, of course.
Presentation? There is a there was a slide where you had an assumption. Yeah, this one. So okay. We have an distribution of noise, normal distribution of noise with zero mean and sigma squared variance. And we have the next line, Y has a distribution of normal distribution with mean X multiplied by beta. What is X multiplied by beta?
So X here is our data that we have and know.
But X is a matrix and beta is a vector, so it means that.
Exactly, yeah. So this is so-called multivariate normal distribution. It's not.
What is sigma squared then? Sigma squared is just a number, but we have we should have a covariance matrix at least.
Yeah. So here it's let me.
So should it sigma squared be like a unit matrix multiplied by sigma squared or something?
Yeah, I think that's maybe a better explanation for better thing for it. I just maybe simplified it a little bit, so it's like diagonal matrix with zeros at all. So yeah, you're right. Maybe it would be better to multiply the identity matrix by sigma squared. So it would mean that our attributes do not have correlation. Yeah. So
and as far as I know, ordinary least squares has this assumption that noise is independent.
Yeah.
Okay.
Yeah. Right. Okay, so any other questions?
Are there any other types of regularization besides the most popular ones?
Well, as I described, ElasticNet can be described as a third type, but it's the combination of those two, so it doesn't count. I believe in the regularization in this way, like plus, just give me a second. Like in this way, when we summarize additional like coefficient multiplied by the sum of some coefficients, I think there are not like famous regularizations of other types like this. In some other algorithms, regularization may exist in different ways. Yeah, so I'm like not prepared to give you maybe an example, but okay, the simplest example actually of another type regularization for regression is this. Let's have decision tree regressor. This is a regression algorithm, and it has regularization itself. What is regularization for decision tree? It's actually pruning parameters. So the maximal depth of the tree is regularization parameter. The minimal number of objects in a node to split the node is regularization parameter. So other types of regularization for regression are possible. It's just, you know, it can be expressed in a different way.
Okay, and for instance, we can also use some conditions, just some custom conditions, maybe according to the features. I don't know, maybe that's also a variant.
I
so
don't
for example,
think,
we choose just some specific features just to impose maybe some restrictions.
Yeah, okay, I understand what you mean. It's just it's hard to find a good reasoning to do that, like to mathematical formulation, so it would work. Maybe there are some ideas to try this, and some of them may actually be like working, but I'm not familiar with them, I think. So it's something that you could try to find for yourself to see if there are some success in applying absolutely new or different regularizations.
Okay, thank you.
I see, I think the question chat, yeah. Basic question of splitting the data in train plus validation plus test. Let's say we choose to tune one hyperparameter for a model. Are we going to try a few values of the hyperparameter on the train data and validate it on validation data? And why do we still want to validate it again on the test data? So idea here is to simulate real world. In real world, what happens? We have a task or a problem, and we have data for this problem. But our goal is not to solve the task for this data that we have. Our task is to solve the problem for new data. Yeah. So new data would behave according to our model, and this new data we do not know. So usually what we would do, we would split known data into train and validation. We would use training data to fit the model, and we would check the results on validation data. Yeah, and if we see the good results, then we apply it on test data. However, there is a caveat. If we do it like I described, no one guarantees that actually the model that we fit is good for new data. What we actually did is to find the optimal hyperparameter which is good for validation data, because we check this parameter for validation data. And there is no guarantee that it is good for any new data that we do not know. So instead of doing this, we split the data into 3 parts: train, validation, and test. We do the same with train and validation, but after we're done with that, like we already determined the ideal model, the ideal parameters, we check this final model against the test data. In this way, if we get good result on a test data, we now have some guarantee that our algorithm, our model does not break when something unknown is coming up our way. So this provides us like additional guarantee that we not just found the best parameter for some bunch of data, that we found the hyperparameters that are good, or one, in your case, one hyperparameter for all possible data.
Okay, well, I have a question related to that. So let's say that we find the best parameter, hyperparameter when we test on validation data. So why don't we retrain the model again with trained data and validation data as well, so that the model would be better for test data?
If you get the final model with final hyperparameters in the end, you can train it again on the whole bunch of the data that you know. Yes, if you're already sure that this is a good parameters or hyperparameters. But before that, you have to be sure. So you do all this thing. As it was mentioned in the chat, doing actually train and validation, scaffold, cross-validation, also good. Also a good thing. But just in the end, when you found optimal hyperparameters, you just check it, like make a final check against test data to see that you didn't find hyperparameters that are just good for this bunch of data, but you found hyperparameters that work for any situation. Although I got a lot of your support in this discussion forum, I'm still stuck in the NA question week 1. Would you please give some other hint on this question? Unfortunately, I am not the creator of this test, so this is Maxim. And the NA question, can somebody tell me the number of this question, so I just maybe check it real quick. Question 1. Week 1. Let me see test here. So what is the question that is problematic?
I think it's the question where you have to where you have to write letters and numbers.
Letters and numbers.
It's quite random. I think it's I only got the right answer just out of pure luck. So I know why this person doesn't know.
Is it number 20? What numerical feature has the largest mean value, or like I'm just number 5? Yeah, I see. You see in the chat. Sorry. Assume I have data set. The amount of data is 1000. Okay, several ways to handle missing data. For each feature, choose appropriate way of handling missing values. Okay. I see that. Which feature? All right, so just maybe some hints how to do this. Let's go through the ways as an explanation. So deleting feature. Deleting feature is bad for us because we lose information. But in some cases, the feature already does not have a lot of information. When does this happen? When we have a lot of missing values, for example. Yeah. So this is a good like hint already where to apply this way. Delete observations. This way is good, but when we have rows or objects with several missing values. So if there are, if there would be like description, if the description would say that several objects have only one of the 5 attributes, you would know that these objects are not good to, take into account, and you can delete these observations. But I think the second way is not applicable in here at all. Fill with mean value. This is applied for continuous data because discrete data does not have average value. Fill with moda applied to categorical data because moda cannot be calculated for continuous values. Create new category for missing values might be good for any categorical value, maybe even for any categorical and numerical value. Here you actually have to ask Maxim what does he mean by that. So what would be better, to create only for categorical or for any possible feature? Create new feature is missed. I think it's the same. I don't understand the difference. Again, this is for Maxim to answer. Interpolate by machine learning. I think this is a good way for anything, for any feature except the features that we deleted. So if you have appropriate algorithm, you can use it. Maybe Maxim here meant the exact interpolation algorithm. In that case, it is only applied for continuous data. So I don't know if my arguments here are wrong or right, but you can use it maybe as kind of hints to answer this test correctly. All right. Any other questions? Okay, I think no more question. Thank you for listening to this webinar. Hope it was useful. Yeah. Okay, thank you and good luck.